about diagonalizing a matrix. A square matrix A is said to be diagonalizable if there exists an invertible matrix P such that A equal to P D P inverse, where D is the diagonal matrix. Now note that all matrices are not all matrices can be diagonalized, and let A be a square matrix with eigenvalues lambda 1, lambda 2 and corresponding eigenvectors x1, x2. Then you can write A as P D P inverse, where P has the eigenvectors of A as its column vectors and D equal to a diagonal matrix having lambda 1, lambda 2 the eigenvalues as its diagonal elements. So let's go through a small problem. Diagonalize A equal to 2, 3, 0, minus 7. So first we write determinant A minus lambda I is 0. So we get determinant 2 minus lambda 3, 0 minus 7 minus lambda is 0. So expanding you get the eigenvalues as lambda is 2 and minus 7. When lambda is 2, A minus 2I will give you 0, 3, 0, minus 1. You can just substitute lambda is 2 here. And A minus 2I into x1, x2 will give you 0, 3, 0, minus 9 times x1, x2 is 0. So multiplying you get 3x1 is 0, minus 9x2 is 0, 3x2 is 0 or minus 9x2 is 0, which means that x2 is 0. So x1 can be any vector, so let x1 be 1. So you can say that 1, 0 is an eigenvector associated with lambda equal to 2. When lambda is minus 7, if I put A plus 7i, I get 9, 3, 0, 0. And we have to find the eigenvector associated with this. So I put A plus lambda I, say x3, y3 is 0. So when you multiply, you get 9, 3, 0, 3 times x3, y3 is 0, which will give you 9x3 plus 3y3 is 0. The second row is 0. So 9x3 plus 3y3 is 0 means 3x3 is minus y3. So if I put x3 as a 1, then I can say that 1 minus y3 will be minus 3. So 1 minus 3 is an eigenvector associated with lambda is 7. Note that you can take any value for x3, 2 or minus 1. So the diagonal matrix is D is lambda 1, lambda 2 as the eigenvalues. So it will be 2 minus 7. It's a diagonal matrix. And P will be, the eigenvectors are the column vectors. What are the eigenvectors? You have 1, 0 and 1 minus 3. So A will be P D P inverse. That will be 1, 0, 0 minus 3, which is P. This is D. How will you find the inverse of P? Determinant of P is